All right, our next presenter this morning is Dr. Tricia Kaiser of Wildwood Consulting.
I know that several of you have seen previous presentations on this project, so some of this is going to be repetitious for you, but there are a few new pieces to look forward to. First, I want to thank the Florida Department of Resilient Coastlines Program for having funded this project. I also want to thank Jessica Beach with the City of St. Augustine and her staff, who were very active participants and contributors to this project. And I think that they were really key to making this as useful as it was. And I also want to thank Dr. Bean, who was my technical advisor for this project. So a little bit about the project. First of all, the reason for this project was we see that vulnerability assessments are most often done for two reasons. The first one is to look at the vulnerability of publicly owned infrastructure, such as roads and emergency services, or even major wastewater facilities, wastewater treatment facilities, and their vulnerability to climate change related impacts, such as sea level rise. We also see that vulnerability assessments are often used to understand how vulnerable water bodies are to septic system pollution potential. But we don't often see how the septic systems themselves might be vulnerable to climate change related impacts. And this is kind of a loophole or falling through the cracks kind of thing, because septic systems are privately owned. So they're owned by the property owner as opposed to being a municipal infrastructure service. And so we haven't really seen a whole lot of vulnerability assessments of the systems themselves and what their vulnerability is to climate change. Because of course, if they are inundated with either sea level rise or rising groundwaters, then they are going to fail to operate, and they release all of their contents to the land surface, causing human health and environmental hazards as well. So this project wanted to look at the vulnerability of the septic systems themselves from climate change related impacts. So we developed a vulnerability assessment method. For fun, we calculated some nitrogen exports using the ARC inlet tool. We paired that up with the vulnerability assessment scoring, and it was very informative to show where systems were both vulnerable and exporting nitrates to surface waters. Part of the project was a report on the state of wastewater treatment technologies, and this also did include costs of various systems, estimates, of course, and a whole long list of funding opportunities. And then, of course, we're sharing this information wherever possible in the different presentation formats. This here shows the data that we used for this project, and this was all publicly available data. So NOAA data, USGS data, property appraiser data, and how we use that in both the vulnerability assessment and the ARC inlet modeling. When we developed the vulnerability assessment, it was with key inputs from St. Augustine staff. They identified these 4 parameters as what they felt was the most important for understanding how septic systems and their water and wastewater treatment area would be vulnerable. These include the combined parameter of storm surge and elevation, soils using the USDA's sanitary soils for Florida layer, how groundwater is rising, how fast it's rising, and then possible exposure to sea level rise. So I want to point out the sea level rise parameter gets a lot of questions because people wonder why 1 foot of sea level rise is ranked as the highest risk as opposed to 3 feet of sea level rise. And understandably, 3 feet would be very bad. Nobody wants to be inundated with 3 feet of sea level rise, but it's more likely that you would experience 1 foot much sooner than you're going to experience 3 foot. And so that makes 1 foot of sea level rise a higher risk than 3 feet of sea level rise. For the weight rankings, here again, it's a little difficult to decide which one of these parameters is going to be most bad. So we looked at identifying those that are more imminent or are already being experienced, and that includes the soils, So most of the study area is under the severely limited soils ranking system from the sanitary soils layer. And the rise in groundwater is most likely to happen before sea level rise inundation takes effect. And so soils and groundwater got a higher weighting than the storm surge elevation and sea level rise parameters. This is, I know it's hard to read, it's just to kind of show you how each of those 4 parameters were impacting the septic systems in the study area. I want to point out that, again, the distribution of the severely limited soils in the top right, the red dots, there's lots of those all over the study area. And then in the groundwater rise in the bottom left, there's a lot of those systems that fall within the groundwater rise parameters in the category 3 ranking system. So this is the combined parameter of the vulnerability assessment scores. And this was, calculation method for this was to take the parameter rank and multiply it by the weight for each of the 4 parameters, and then add those 4 products, the products, multiplication products together to come up with the vulnerability scoring system. So I hope that this is fairly intuitive. Red is bad and blue is less bad. So we see that most of our high vulnerability scores are up in the northern area of the study area and along the San Sebastian River, which is kind of angled through the middle of the area. And then the less bad scores are in the Salt Run area and the West Augustine area. So for the ARC inlet model, this is a tool that was developed by Dr. Yee and his students at FSU, and this estimates the nitrogen exports to water bodies from the septic system locations. So we used, for the most part, the standard input parameters. The only one that we changed was the smoothing factor of 50. So the results from that is, it shows that the Salt Run area and the southeastern portion of the study area has the highest nitrate exports in this study area. And I want to say that just because it has the highest exports doesn't mean that it necessarily meets the criteria for being a TMDL or a potential BMAP area, just that in relation to this project, it had the highest exports. The second highest is the Stokes Creek area, which is again in the northern section of the study area. Now, combined, all of these mass output loads in pounds per year, roughly equal about 2% what the municipal facility puts out. And that was noted by the city manager at a commission meeting last year. Now, the Salt Run area, again, this doesn't mean that it meets any TMDL criteria, but he also said that that is roughly 1% of the total outputs for nitrates of the municipal facility. So the groundwater rise, now this became, I almost want to say the star of the show, except that it's not a good star, it's kind of a scary star. The groundwater estimates really came out as the most risk-oriented or the most threatening parameter of this project. We estimated the rate of groundwater rise by using St. Johns River water management data for an 11-year period that had been collected daily, I believe. It was daily or monthly. And we looked at how it changed over time. So we calculated the average change over the entire period. And then because there were only 2 groundwater monitoring stations in the study area, we interpolated that change across the study area. We see that all of these septic systems in the study area are estimated to be inundated with groundwater rise in the next 4 to 37 years. So when you consider that the life expectancy of a system itself is supposed to be about 30 years, then you can question whether or not it's ideal to put septic systems in at all at this point. Here, I just wanted to show, lay these 3 pieces of information next to each other. And again, I know because of the screen, it's going to be hard to see, but we have the vulnerability assessment scores on the left, the nitrate export estimates in the middle, and the groundwater inundation estimates on the right. And so all of these things, we can see that they're all starting to line up. So Stokes Creek in the north and down the San Sebastian corridor are areas where we see high vulnerability and definitely high groundwater risk. And then nitrogen exports, again, in the Stokes Creek area, a little less so in the San Sebastian, but high again in salt red. So some really important takeaways from this project was that the vulnerability assessment scores told St. Augustine where their critical septic systems were and which ones were showing a high vulnerability to failure driven by climate change related impacts, such as storm surge, high tide flooding, sea level rise, and groundwater rise. Coupling that with the ARC inlet modeling also gave them great information on where they could focus efforts on future septic to sewer conversion projects, or where maybe it wasn't quite as critical because they might have lower exports or they might have had lower vulnerability scores. Here again, the rising groundwater was really the most informative piece of this, and showing where those systems could face, I don't want to say imminent as in tomorrow risk, but a near-term risk for failure due to groundwater rise. So what has been really cool, I'll skip this slide. What has been really cool about this project was St. Augustine has been able to use the data from this project right away. Right away, they were able to see that the Salt Run area with the higher exports, higher nitrate exports, was an area that they wanted to prioritize for septic to sewer conversion. And so they've already begun those conversations and that process. Also, it showed with those Stokes Creek area septic systems that those really need to be converted, but that actually lies outside their municipal boundary, and it requires the cooperation of St. Johns County. And so they've, of course, begun conversations with St. Johns County about looking at doing septic to sewer conversions there. Another benefit of this project was they were able to use the data right away in different grant applications. And one of those key ones included to put in more groundwater monitoring stations. So I mentioned that there were only 2 stations within the study area. Now they have grant funding to go put in more stations. They're going to be able to monitor the groundwater elevation and how fast it's changing, as well as nitrogen levels at that groundwater elevation. So once we get some of that data coming in, we're going to be able to go back to the estimates that I had done and calibrate those to get really good formulas to estimate the rate of groundwater rise. Also, Northeast Florida Regional Council and others around the state have heard about this project, and there's been some discussion about repeating this project in other locations. What's really cool is this project is entirely flexible and adaptable to different locations. The 4 parameters that we used in this vulnerability assessment can be swapped out for other parameters that might be more important to your location. So if rising groundwater is not an issue for you because maybe you're inland and you're just not at the coast with low elevation, that can be swapped out for another parameter that would be more appropriate for your location. It's pretty easy to do. Again, this one was all with publicly available information. It could be done with other data if you had it available, but it can be done anywhere. It doesn't even have to be in the state of Florida. So we could repeat this project at another location using parameters that were relevant to you. And actually, that's my last slide. So thank you again to Florida Department of Environmental Protection and the Resilient Coastlines Program for funding this project, and all of the participation with Jessica and the staff with the City of St. Augustine, and to Ebba Bean, my advisor. Thank you.
Thank you so much, Dr. Kaiser. We do have a couple of questions in the chat box for you. I'm going to go out of order with the questions because I think this first one is relevant to what you just shared. Could you explain more about the weightings of the components in the total score, whether it was just a multiplication by the percentages on your, and then also as a follow-up to that, in retrospect, would you change any of the weightings?
Okay, so the setup of the scoring and the ranking. This was, I'm trying to think of how to say this in a way that makes sense. I can see it in my head. So we took the value of the rank parameter and multiply it by the weighting. And then we had, so you end up with a product, a multiplication product for each of the 4 parameters. And then we added those together. One of the parameters that really influenced the distribution of the scores was that sanitary soils layer, because most areas in the study area were within the same soil ranking, the severely limited ranking. And so that, that elevated a lot of the scores just because of that value. Another thing that was really interesting, so the combined parameter of the storm surge, this is inundation from a category 1 storm surge effect, if that parcel, that location was going to be inundated. And then combined with the topographic elevation of the parcel. So if the parcel was at 7 feet or less in topographic elevation and was within the area that was estimated to be inundated with storm surge from a category 1 hurricane, it received the high ranking of 5. We found afterwards that actually there were a handful of parcels that were within the lower elevation, but didn't fall within the category 1 storm surge area. So they had the low elevation, less than 7 feet, but were just outside of the storm surge boundary. So they ended up falling off in that parameter and got a 0 for that parameter altogether. So we didn't account for low elevation, but no storm surge. So that one could probably be put back in, and maybe that would go for 4 because we just used 1, 3, and 5 in that parameter. Could be interesting. Some other parameters that were not included that would like to be included in future studies are the social vulnerability parameters, areas where residents who are on septic service may not have resources in the event of an inundation or even just a compromise. Those would be really helpful in also identifying areas that could be addressed for septic to sewer conversion.
The next question that we have for you today, Dr. Kaiser, is what is the source of rising groundwater?
The source of rising groundwater. So groundwater is fresh water, and salt water is heavier than fresh water. So what happens is your salt water pushes up from underneath and it raises the groundwater above it because that fresh water is lighter weight than your salt water. Also, rising groundwater can happen with increased precipitation. And so with these climate change related impacts, we're seeing both increased precipitation from storm events, just even everyday storms, as well as that groundwater being pushed up with that seawater comes in from the side.
So would it be, I'm trying to tie this into another question, would the rising groundwater data that you're collecting add to how the Florida aquifer is rising as sea level rises, and that is ultimately being included in your equation?
I'm sorry, I'm getting really bad feedback on your audio.
I will make it a shorter question. Is the Florida aquifer rising as the sea level rises something that has been added to any equation?
I don't think that I could answer that question. I haven't looked at how the aquifer itself is changing in relation to this. We would expect to some extent that the aquifer may become more saline, increased saltiness as that sea level pushes in laterally, but I haven't looked at that.
And then one more question in the chat box for you, Dr. Kaiser. A comment that this study is very concerning. Would you be able to comment on the quality of our drinking water?
Well, I am happy to say that DEP took over the septic permitting last year, and they have been looking at starting new studies that look at our current siting regulations. So you can't put septic systems closer than 75 feet to a drinking water well. And, they're looking at, is 75 feet enough? Should it be farther away than 75 feet? How close should it be to a water body? Because those nutrients move laterally as well as vertically, depending on the saturation of the soils, or did you enter a groundwater resource? So how safe is our drinking water is really going to depend on where you are in relation to septic systems, and are you using city water or are you using well water?
Great. Thank you so much, Dr. Kaiser.